In this talk, we present some of our results about weighted limits of classifying toposes and morphisms between them induced by interpretation. An interpretation of a geometric theory into another one is just a morphism of sites between the respective syntactic sites. So our aim is to describe a geometric theory which is classified by a weighted limit of this kind. The motivation of this work is that this logical approach allows us to describe the weighted limits of toposes in a simpler way than through the geometric perspective addressed in the literature, where same weighted limits of toposes are presented as category of sheaves on same side Cj, where J is a Grothendieck topology generated by same covering families in C. And in general, it is not simple to describe all the sheaves which are coverings for such a Grothendieck topology. Moreover, we know that the probability problems are equivalent in a constructive way to generating topology problem. So this logical approach should be more natural than the geometric one. Now we introduce an example of a weighted limit that which is presented in using the geometric approach. So by a comma topos, we obviously means a comma object in the two category of Grothendieck toposes. So this means that if we have a pair of geometric morphisms F and G, then a comma topos is a Grothendieck topos, denoted in this way, which is universally equivalent with a square of this form. A presentation of this comma topos was introduced by Deligne, and more specifically, under the assumptions that F and G are induced by morphisms of Cartesian sites, he presents this comma topos as the category of sheaves on the side D and JD, where an object of the category D is a triplet of this form. An arrow is again a triplet, such that the opus square commute. And then the topology J of D is the Grothendieck topology generated by covering families of the following three types. Now, we don't give another details about this construction. However, it is immediate to see that it is not simple to describe all the sheaves which are covering for this topology. And as we will see, using the logical approach in the sense that we assume that F, E, and G are classifying topos of same geometric theories, and that F and G are induced by interpretation, then we can describe a geometric theory classified by the comma topos of F and G in a very simple way. And so we can present this topos as the category of sheaves on the syntactic side of this category. Now we proceed to recall the same necessary background. Given a geometric theory T, a classifying topos for it is a Grothendieck topos, which we denote in this way, such that for every topos H we have an equivalence between the category of geometric morphisms from H to the classifying topos of T and the category of T models in H. Moreover, it is required that this equivalence is natural in H. It is well known that every geometric theory T admits a classifying topos, which can be constructed as the category of sheaves on the syntactic side of T, and that every topos is a classifying topos of same theory T. Indeed, the Diaconescu equivalence provides us an equivalence between the category of geometric morphism from H to our topos and the category of J-continuous flat functors. And it is possible to describe a theory whose models in H are exactly these J-continuous flat functors. Now, we consider a weighted diagram valuing in the two category of Grothendieck toposes. So this is just a pair of two functors of this form. A weighted limit for such a diagram is a cone which is universal. So a cone for such a diagram consists in a topos H together with a pseudo-natural transformation in this way. And the universality means that for every topos H, we have an equivalence between the category of geometric morphism from H to the vertex of our weighted limit and the category of cones with vertex H. Moreover, one half of this equivalence is the functor defined by composition with the universal. It is known that the two category of toposes admits all finite and small weighted limits. To see this, we can resume these two results, which state that small or finite weighted limits can be constructed from small or finite products, equalizers, and cotensors with two. Maybe we recall that in an arbitrary two category, the cotensor of an object with two is another object, which is usually denoted in this way, which is universally equipped with a diagram of this form. And 2 is just the category with the two objects and exactly an arrow between them. And the two category of toposes has all these structures. Now, we mentioned before that an interpretation of a geometric theory into another one is a morphism of sites between the respective syntactic sites. It is known that a morphism of site induces geometric morphisms whose inverse image restricts to the underlying functor of our morphism of sites. In other terms, we have this diagram commutes, where the vertical arrows denote the canonical functor, which are inclusions, since the syntactic topologies are subcanonical. And geometric expansion of a theory T is a geometric theory T, denoted in this way, which can be obtained by adding to T source, relation symbols, function symbol, or half symbol. Now, in order to describe a theory classified by a weighted limits of classifying toposes and interpretations, we can argue as follows. First of all, we consider the universal property of classifying topos, from which we can deduce that the category of geometric morphisms from H to our weighted limit is equivalent to the category of models in H for a theory classified by our weighted limit. Moreover, by the universal property of weighted limits that we recorded before, we have an equivalence between the same category and the category of cones with vertex H. So, putting together these two equivalences, we can regard a model for a theory classified by our weighted limit as a cone with vertex H. And it is possible to describe a theory whose model are exactly these cones. More specifically, it can be described as a geometric expansion of every T, where T is a theory classified by, Tj is a theory classified by Tj. So here there is just a list of same weighted limits that for which we can specialize and adapt these general constructions. In the rest of this presentation, we will consider comma toposes, fiber products, and small limits of toposes. So here I will just written the universal property of the comma topos, which I don't read. So by this one-dimensional universal property, by this one-dimensional universal property, we can describe models of a theory classified by the comma topos of F and G as a triplet of this form, where M is the T-force model which corresponds to these geometric morphisms, N is the T-second model which corresponds to these geometric morphisms, and eta is the homomorphism of T models which corresponds to the natural transformation of. And now we see that we can describe a theory whose models in an arbitrary topos H are exactly these models. These are models of this form. So we start to assume to have a comma topos with the property that F and G are induced by interpretations. Now we start to consider this theory, which is built over this signature. We have embedding of this form. Moreover, we have our interpretation. And we consider a sort in a sigma. Here, now we consider the formula 2 in the context of a variable of sort A, and this object is sent like this. Now we have, by our assumptions that P and Q are induced by morphisms of side, that this is equal to G. And since this object belongs to the syntactic category of the second, this is equal to same classes of formula in context. And similarly for the case of P. At this point, we embed these two objects in this syntactic category, and we force the existence of an arrow between them. To do this, we can add a relation symbol R of A, where these sorts are those which involve in the context of these two formulas, and the following three absence, which force the relation symbol R of A to be provable functional from this formula to this one. And moreover, we have to force the conditions in terms of commutative diagrams which appear in the definition of homomorphism of models. To do this, we can add this absence for every, and we have to repeat this argument for every sorting in sigma. And so now we can add this absence for every function symbol f, where delta theta p of f is a representative of this arrow, and similarly for this one. And for every relation symbol, we can add this absence. Maybe we see that this absence forces the existence of a commutative diagram of this form. Where here we take a representative of this subobject. No, sorry. Of this subobject. Real context. And this option forces the existence of an arrow in this way, which makes this diagram to commute. And so this is a theory classified by the comma topos of F and G. Now we see that we can describe a theory classified by the fibred product of these two classifying toposes by adding actions to the previous theory. Indeed, by the universal property of the fiber product, we can describe a model as a triplet in this way, where here eta is an isomorphism of T models. So, in order to obtain a theory classified by this fiber product, we can add these two options, which force the R of A to be a probable functional formula also in the reverse direction, and this option which force the existence of an arrow, of a dashed arrow in this way, which makes this diagram to commute. Now the last result that we present concerns small limits of toposes. So now we proceed in similar way. We consider again that by the universal property of our limit, we can describe a model of a theory classified by this limit of classifying toposes as a collection where each HE is a TE model image, such that we have an isomorphism between the model which corresponds to these geometric morphisms and to the T model which corresponds to these geometric morphisms. And to do this, in order to describe a theory classified by this limit, we can argue in a similar way as we did before. So we add a relation symbol which forces the existence of an arrow between this object and because here we have we start to consider this theory built over this signature, and we consider this embedding moreover we have our interpretation P of S. We take as before this object, we embed this in this signature, in this syntactic category. Here the image of this P of S since it belongs to a syntactic category, it is equal to same classes of formula in context. So we add now we embed these two objects in this syntactic category, and we force as before the existence of an arrow between them by adding a relation symbol, where these sorts are those which involved in the context of this sort of this formula, and AJ is just the embedding of A in this signature. And to conclude, we have to add the the axioms which force this relation symbol Rs of A to be probable functional in both the directions. So we do this for every arrow S in E and for every sort A in sigma j. And to conclude, we had to add the condition as before, which force the conditions in terms of commutative diagram which appear in the definition of homomorphism of models. And that's good. Thank you very much.